So today I'm going to talk about the 360 VR, how we have built the pipeline at Yahoo. So myself, I am Satender Saroha. I'm Director of Engineering in the Video Platform Group at Yahoo. I also consider myself as a VR enthusiast who has led a team of passionate Yahoos inside, across the board in marketing, sales, production, who have built this whole pipeline to be able to stream 360 videos. So before I get into the pipeline, I just wanted to share this quote from Chris Milk about the power of virtual reality, which is when he says that it's a technology that could actually allow you to connect on a real human level. And this has been a craving of all human beings when it comes to media, starting with print, then it went to photos, then it went to videos. And we believe virtual reality is the next truly immersive medium where you feel like you're almost there. And this has been showcased through a lot of movies which have come out. Chris Milk has produced, and they have won awards at like recent Grammys. So we feel this is just the tip of the iceberg. This is just starting point, and a lot remains to be done in the virtual reality space. All right, so today's talk is not about trying to convince you about the power of virtual reality, but more about what did we do technically in terms of building our whole pipeline. So we're going to cover the 360 streaming workflow, how we added that to our existing video encoding pipeline. And there are really two main steps where we made the biggest improvements or the biggest changes. One is in the stitching step, and the other is in the player rendering. Then we are going to cover, apart from 360, how mobile VR itself is a very engaging medium where not just about 360 videos, but in general, how you can provide room scale experiences using mobile VR, which is a step which is different than like your traditional headsets like Oculus Rift and Vive. And then lastly, we are going to cover, which is the most interesting part of this talk, I would say, is the challenges which are there existing in delivering 360 streams and how we have overcome some of those and how a lot of work still remains to be done in that space. All right, so this is our high-level architecture diagram of the 360 streaming workflow. So it starts with capturing the whole 360 view using different camera rigs. We have our own 12 camera rig using GoPro cameras. From there, you are taking images across the whole 360 spectrum, then feeding using HDMI output through our manual capture cards into our stitching box. And then the meat of the work happens in the stitching box, which is the blue box there. And from there, once the whole image has been stitched, usually we stitch in like equirectangular projections. That MP4 is then ready to be output as an RTMP output to our regular live origin servers. So that's where our regular video pipeline takes over. And from there, it's converted into multiple bit rates like HLS streams. And then it's shoved into the CDN. And then the other big change which happens is on the player side, the rendering side, where we have players not only on desktop but on mobile, like using different cardboard VR or Gear VR, and also on mobile web, like on Safari, where we stream our own player, like the JavaScript player. All right, so let's get into the meat of like what are the fundamental things needed to do a good quality stitching. So stitching really is a three-step process. The first step is the raw frame image processing. Here what really happens is it converts an uncompressed raw video data to RGB, and this involves steps from black level adjustment to demosaic algorithms in order to figure out the true RGB color parts for each pixel based on the surrounding pixels. And the goal of this step is to apply sharpening and noise reduction algorithms to enhance the image and suppress the noise. Then the second key step is the calibration step. So like here we have taken like 12 images through our GoPro cameras, and we have produced a stitched output on the bottom. Calibration is the key here. Its responsibility is to avoid the vertical parallax while stitching the overlapping portions. So in this process, what we are trying to do is align everything in the scene so that both eyes see every point at the same vertical coordinates. And this step essentially matches the key points across different images amongst the adjacent cameras. So you ends up using different computer vision algorithms like BRISC and AKs. And at the end of the day, like I said initially, it's trying to avoid the parallax when it's trying to stitch the images by identifying the key points. The third important step is the optical flow. This is really interesting. So you can have like 8 cameras, 10 cameras, but still there are gaps between the cameras. So optical flow's job is to cover those gaps between adjacent cameras by providing an interpolated view to create virtual cameras between those spaces. And so optical flow algorithm is finding the patterns of apparent motion of image objects between 2 consecutive frames, and then sort of trying to create, by using interpolation, those virtual spaces. And again, it uses OpenCV algorithms to find the optical flow. For our use case at Yahoo, we have integrated with third-party software called Vahana VR for live streaming. And as far as VOD is concerned, we have modified the Surround 360 software, which is available as open source, to make it work with our GoPro cameras. And essentially, we have had to make changes, optimizations in the 3 steps, like I called out: raw frame image processing, calibration, and optical flow. There is another software which is gaining popularity, which is called Radeon Loom. And this is available from AMD. The only caveat there is you have to use their GPUs. We are currently using NVIDIA ones, but this is tied to their particular GPUs. But this looks very promising. This came out like a couple of months back. All right, so now that you have a 360 stitch stream, the next real challenge is how to render it on the player side. So there are really 4 main steps involved on the browser or on your device which are involved while rendering the 360 stream. The first is you get this stitched equirectangular video as a source, and then you create a sphere, and I'll get into how we create a sphere, but these are OpenGL concepts. You essentially create a sphere and apply the equirectangular video as a texture on top of the sphere. So you're extracting it from the frame and applying it as a sphere. And then you create a camera in the middle of the sphere, in the center of the sphere, and from there you can have different user interactions to control the motion as you're moving around either with your mouse or your head. So just to get a bit deeper into the player rendering, like I was saying, we use WebGL, which is OpenGL on the web, and Metal for iOS. Metal is an equivalent pipeline, equivalent to OpenGL, but much faster on iOS devices. From a concept wise, you can think of like GL renderer is an object which is responsible for rendering the scene, and it has access to hardware accelerated 3D rendering. Now what is a scene? A scene contains multiple 3D objects, and a 3D object is where you have like a geometry, like you can create different shapes like sphere, cube. In our VR case, we are creating a sphere. And then you have a material like what the object looks like. So here, like when we are capturing the texture which we have extracted from the frame, we combine this material and geometry into a mesh. And so scene effectively ends up containing these 3D objects in form of a mesh. And then you have a camera which uses different perspective positions, which is designed to see the way the human eyes see. And you can have like a near plane, far plane, those kind of concepts. So when it comes to rendering, there is a renderer which renders the scene, and the scene itself contains these 3D objects and the camera. So that's how the whole picture comes together. To get a bit deeper, I'm just showing you the images here. So this is the raw 360 stitch stream, which is the equirectangular format. Now I was talking like there is a sphere, an empty sphere, and on that you are wrapping the particular material, which is our texture. And then from the camera perspective, camera is really like a showing you a view of a frustum. There is a near plane and a far plane. And effectively, it's able to show anything which is between those planes. And then you can, moving around, you can zoom in to particular portions of the texture which is available on the sphere. So this is showing like a car and the deeper points of that. So let me just show you a demo here, if I can reach. Okay, so I'm just going to show what we were talking about there, and just a sec. Can somebody help me? Just a sec. I'm not able to see the. Okay, need to detect and drag. Okay, so here we are capturing a particular field of view from the camera. So as I move this around, I'm trying to show like the line of the camera can be changed to show you different portions of the video which is being played back. So effectively your field of view can be modified as you're moving around, and this is how the actual rendering when the user is watching the 360 video is happening. All right, so coming back to okay. Now let's get into, so far it was all about 360 videos. But there is a whole level of immersion you can achieve just from 3D VR, especially on mobile devices. And we have done some good work in the mobile side, enabling true 3D VR room scale experiences. And we are using it especially for providing immersive sports VR experiences, where you're sort of in a lounge, and the image you are seeing there is coming straight out of our app, like which we are developing for sports VR. It's not in production yet, but essentially showing the Warriors game last Sunday in a room kind of experience where the users are sitting on the bar on the left side. And this whole experience has been developed using Daydream VR plus the Unity SDK. And there were quite a few challenges we had to overcome in order to provide true motion to photon latency to provide a true 3D VR experience on the mobile. All right, let's get to the next interesting portion here, like different challenges which are there in the 360 and the mobile VR space. So we'll start with, like I was just saying, building the mobile VR experience. The biggest challenge is to do the true motion to photon latency on mobile. Here, the latency between the physical movement of a user's head and the time it takes for the updated photons from your head-mounted display to reach your eyes, that is what is called as motion to photon latency. And ideally, this should be less than 30 milliseconds. True devices like Oculus Rift, Vive, they already provide it less than 25 milliseconds. But all the mobile devices, usually especially the WebVR, have a latency of approximately 90 milliseconds. So how do we solve this, or what is the real challenge there? So traditionally on mobile devices, rendering is double buffered, which essentially means there are two buffers stored in GPU memory. One that is currently being scanned out. So there are two steps, rendering and scanning out. What you see on the display is what is getting scanned out. So that scanned out display is called front buffer, and one that is being rendered to is the back buffer. So at each frame display, the two are swapped. So the GPU never renders the same buffer that's being scanned out. So this has the advantage to prevent the artifacts. But at the same time in VR, because we are trying to show as soon as the user moves his head, the side effect is this leads to increased latency. So an alternative approach is to what we call as single rendering is to render directly to the front buffer, but time things out so carefully so that you have rendered each line of the image just shortly before the scan out is going out to the display. So here we use a technique which Daydream provides called scanline racing, and essentially scanline racing is a process of knowing where the scanline is in the screen and just rendering before that, not overshooting that to avoid the artifacts. So that solves the problem of motion to photon latency by going for single rendering on top of scanline racing. And we have used it using the Daydream VR SDK for our sports VR experience. Now let's get to the challenges in the 360 space. So 360 videos, for the most part, all browsers support it, except for Safari on mobile web, which is a big portion of the iOS traffic, especially if you're just trying to see an ad in the middle of the browser while you're watching some other content. So the challenge there is there's a coarse bug where Safari does not respect the coarse headers. These are the cross-origin request headers. Essentially, usually whenever a video is played back, your player is in a different domain than the CDNs from where the bits are coming. For some reason, when WebGL is in the mix, Safari is not able to respect if the video is coming from a different domain than your player. And as a result, it's unable to draw content to canvas. So one of the things we have implemented is which is still a workaround until the real bug is fixed. This bug has been open for a couple of years now, is to embed our player in an iframe on the same domain as CDN. The alternative could have been we use a reverse proxy to proxy our mobile web traffic to just the CDN through our own servers. These are not scalable things, but at the same time, these are good workarounds as long as the amount of traffic which is being served on mobile web just for 360 videos is not huge. Okay, now comes the most interesting challenge, which is about the huge amount of data you need on 360 videos. And this is one of still the unsolved problems of the day, where when you talk about immersive VR, the more immersiveness you want, you are trying to provide like 8K kind of experience per eye. And if you think of different field of views where you're trying to provide this 8K, like if you're moving around, like let's say 4 different areas in the 360 video, the challenge gets much more complicated. So you almost need easily more than 100 Mbps, even up to 200 Mbps if you were to do a perfect job with the current technologies. Whereas the average Wi-Fi is about 20 Mbps in US. So what do? The typical solutions are like, first is compression. So like I was saying, when we are stitching our video, we use equirectangular format. There is another projection called cube map, which is of the order of 30% less bandwidth consumption on the cube map format. On equirectangular format, you can think of like it's like a world map, essentially, where the poles have a lot more pixels, even though there's not really that much of information over there. So that causes a lot of this increase in the size of the videos. With cube map, you don't have those issues. Of course, the effect of that is like your player should be able to understand the cube map projection and then being able to play that. The second piece is, like you have heard over at this conference, like VP9 provides 40% reduction of data flowing over the wire compared to H.264, and similar results are there for HEVC. We have encoded our 360 videos using VP9. At least that takes care of this problem on Chrome browsers and the Android devices, which is a huge segment of our overall playback. All right, so next solution for addressing the big data problem is what we call as field of view adaptive streaming. A lot of work has been done in this space in the research, as well as Facebook also does some kind of field of view adaptive streaming. Fundamentally, what it is it borrows heavily from the concept of traditional adaptive streaming. So traditional adaptive streaming is, depending on the network, you serve different bit rates, right? In the field of view adaptive streaming, what we do is, the idea is to serve the video of the same quality for a given bitrate, but divide it into multiple regions with a particular viewport where the user is looking have the highest resolution compared to the rest of the video, compared to the rest of the equirectangular video. So you here are essentially spatially dividing videos into multiple tiles, and then server prepares these n, what we call as quality effective regions videos, and each of them is pre-processed set of tile representations. So then each of these QER videos is then encoded at the traditional multiple bitrate levels, and MPEG-SRD is already there, which describes tile spatial relationships. So you can use that extension of the MPEG- to be able to send those playlists providing the different QER regions in that video. And so then there is an adaptation set for each field of view. So that's the high level sort of approach here. Now this particular image shows you how client can talk to the server and get different QERs. So here S1, S2, S3 are your different segments of videos. You can treat them as like HLS segments, segment 1, segment 2, segment 3. So initially, let's say client connects to the server and he is looking towards the left side and his bandwidth is low. So he is going to get the the QEC2 low particular portion of the video, which has QEC best on the left lower portion. And then when his bandwidth gets higher and he's looking in the front, at that time he's being fed the QEC3 with a high bit rate, and so on. So that gives you an idea of how lower video bitrate is being served depending on the network condition, and different QEC regions are being served depending on where the user is looking at. And when the head of the end user moves, the device extracts a viewport because it has the full spherical video. And if the new viewport center is far from the QEC, we will continue showing the lower quality, at the same time and asynchronously fetch the higher quality QEC from the server side. So he doesn't see a total blank. It's like traditional adaptive streaming. He's seeing a lower quality while the higher quality of that resolution is being fetched from the server side. All right, so a lot of this work is being, I have the link over there, we have borrowed from the research already done, and we are experimenting with this using HEVC for now. Okay, the fourth and the final challenge, this is the holy grail, is achieving 6 degrees of freedom. So traditionally in 360 you can only get 3 degrees of freedom, like essentially you can rotate like up, down, move your head, or just look like this. These are the 3 degrees of freedom. You cannot achieve, like in this video we are showing, the person is leaning back, leaning front, or moving sideways, and being able to provide the specific portions of that video from 360 videos. So this is still an unsolved problem. There are complex solutions out there, or at least which are much more expensive. Like there is a light field camera from Litro, which is order of hundreds of thousands, which cinema folks are using. But there is one interesting research which has recently come out from Adobe, where they claim to have the ability to enhance existing monoscopic 360 videos with 6 degrees of freedom. So here what they're really doing is, using algorithms, they are able to, in an offline way, infer the camera path and the 3D scene geometry using structure from motion techniques. And then they apply in real time on the headset a novel warping algorithm which synthesizes the views on the fly. And using this, they are able to create, sort of just like I was talking about virtual cameras, they're able to interpolate these views, mapping to where you are leaning in real time, and synthesize these new views for each eye in parallel to achieve the stereoscopic rendering. This is if this really pans out, this will be a great thing for all the existing 360 videos which are out there in the market without having to rely on the most expensive cameras. All right, I think that's pretty much as far as what we are currently doing. We used our whole 360 streaming pipeline to do the presidential inauguration. And right now we're in the process of getting our 360 iOS player using Metal instead of Cardboard SDK, which is much more performant out there so that we can use that for our future upcoming events. I think that's pretty much. And thank you. And this is how you can reach me on Twitter and email if you have any questions. Very tech.